Good afternoon. Tonight at 6:30 there is a midterm, the first of three, and you know where to go. I think it's been all posted. It's a 90-minute midterm, multiple choice, 40 questions. All right? The Scantron will be provided to you. The last time we had a review, and by now you should know that you have three principal quantum numbers. We learn about the fourth one today. You describe the probability of finding the electron around the nucleus in terms of quantum numbers. And the first quantum number, n, will give you the energy. It's the principal quantum number. The second quantum number, the angular momentum, will give you the shape. And the third quantum number will give you the orientation in space of certain shapes. If they are radial symmetric, of course, it doesn't really matter. There is no quantum number. But if they are not radial symmetric, then you have orientation in space. So you know how to calculate these orbital energies. If n equals 1, this is the lowest energy level an electron in an orbital can have. Of course, n is different for different orbitals. And you calculate this with they call it in your book, the Bohr's equation. And this is for one electron, system. So it says the energy of the nth level is minus the number of protons, the atomic number, divided by the level number. That's the principal quantum number. Level 1, level 2, level 3, and so on. We did this in the review on Friday. So and this is an energy, okay? You have it in Rydberg. Sometimes the Rydberg is R something, Ry, or we have it here R infinity. It depends who defines it. Yeah? A Rydberg is an energy, and it tells you one Rydberg is 2 times 18 times 10 to the minus 18 joules for one electron, and for a whole mole of electron, it's 1,312 kilojoules per mole. So that's an energy. And you see now we have talked about the different shapes of the orbitals. S have radial symmetric shapes, and if you go higher in n, you can have nodes. You have radial nodes, and with p you have spherical nodes, and you should know all this by now because we have discussed this, as we would say, ad infinitum. You should be able to do this tonight pretty well. So there's one more thing. I think I said it the last time already. If you have a transition from one energy state to another energy state, you can either excite an electron in a higher energy state, let's say from 1 to 2 or to 3 or to 4 or to 5 or to 6, or you can give it so much energy that it will leave the will leave the atom. Then you have ionization. You don't have excitation, you have ionization. And when an electron gets excited, it has to absorb that energy to come between the level it is at to the level where it's going from to, okay? That energy difference. And so when it comes back, that means it emits energy, so you have then an emission spectrum, so it goes from a higher level to a lower level, and what does it emit? Energy, in form of what, for example? That could be light. In the case of emission spectroscopy, it would be light. It doesn't always have to be light, but we are talking about light at the moment, so it emits that energy. It comes from a higher level to a lower level. Then it emits that, and you would see the change in energy, or the difference in energy from that higher level to the lower level is Z squared, so that's the atomic number squared, times the Rydberg constant, minus, okay, the final level is the lower level. We're talking about emission now. And the initial level is the higher level. So it goes from this level to that level. So if n equals, for example, the initial level is the higher level is 5, and n equals the final level would be 3, it doesn't have to go necessarily into the ground state. It can go from 5 to 3, for example. Or I can also absorb from 5 to 3. That's possible. So this is how you calculate that. All right? So if you look in space, you could take a spectrum. And you can take, for example, a spectrum of the sun and you can take a spectrum of visible light. You could also take a gamma ray spectrum, would be also energy. Energy coming from space towards Earth. And if you look at the sun, you see mostly a very complex hydrogen and helium spectrum. You know, I didn't show you a hydrogen atom, exactly how the spectrum looks like, but I've showed you a mercury atom, how that spectrum looks like. When it emits light, it had these 3 lines plus the extra one in the UV, okay? And so every element has a specific, very specific light emission pattern, and even compounds, molecules have also specific light emission patterns. And if I analyze this, and the sun is not actually that interesting, it's huge. See all the lines? Because you have many, many, many excited states there in the sun. And what happens in the sun? That's what we would like to do on Earth. Fusion. The fusion of hydrogen to heavier hydrogen. Or the fusion of hydrogen to helium. Okay? So that means 2 hydrogen go together and 2 protons make helium, all right? So the problem there is, of course, that you have your proton here and your proton here, and you want to fuse that, okay? If I make 2 hydrogen, fuse this, so I have these negative charges of the nuclei. So I can't get them close enough together to fuse. Only if I get them so close enough together that a certain one of the 4 elementary force, what force would that be which has to act? The strong force. It doesn't reach very far, that's why I have to get it so close. If that strong force reacts, then it fuses. And that fusion is then connected with an energy release, all right? So this is what we would like to do on Earth. You need to put in a lot of energy to do it, but then you get more, hopefully, energy out than you put in. That's the concept. That's how fusion would work. So in the sun, it works easily. Why is that? Because you have a lot of energy due to the high temperature of the sun. You have about 10,000 degrees. Kelvin or Fahrenheit doesn't make any difference. In this case, you have 10,000 degrees. And so you do this fusion of hydrogen to helium, and helium-3 and helium-4. And with this, you release the energy. And that's what we see here on Earth. That's why it gets the energy to us. Of course, there are you need to actually have bigger suns to fuse heavier, to make heavier atoms. You need to have much bigger suns. And they have existed, and they still probably do exist. No, probably. I'm not an astrophysicist. So, but there, they fuse heavier and heavier and heavier molecules, the atoms, together to make new atoms. And this goes to about iron. It goes with iron because you get more energy out than you have to put in. So it's an exothermic reaction, essentially. But when you come to iron, after iron, to make gold and silver, you need to have even bigger suns. These are supernovae, okay? And this happened also. So far, actually, we don't really know how these very heavy elements got to us on Earth here. We don't know that. We know how that carbon and hydrogen and oxygen, how this got here on Earth, to Earth. It got through nucleosynthesis, and so stars have deposited this in where the Earth was formed, probably onto the Earth. So we are made out of carbon and hydrogen and oxygen and nitrogen. So most of the compounds in our body are made of that, organic compounds. So we are nothing but a stardust, little stardust. That's what we are, okay? So that's how it came here. Maybe I should tell you that story, that I'm in the business of trying to do chemistry for the first time with new elements. Not that you discover a new element every 5 minutes. It's very difficult to discover a new element. And there was about 10 years ago, there's a research center, it's called Dubna in Russia by Moscow. They made a new element, and they made element 114, and they had a target. That's our target molecules. There's a very thin film of plutonium. Plutonium is element number 94. Is that right? Say yes, okay? It's 94. So if I would be able to put calcium in there, I would get calcium as element what? 20. 94 and 20 would be what? 114. Of course, the probability of doing this is very, very small. So you need an accelerator to accelerate your calcium to very high velocities, high energies, that they can overcome the Coulomb interaction. And when you're lucky, the chance of 1 in 15 probably, you make one atom a week of element 114. And so the IUPAC, this is the International Union of Pure and Applied Chemistry, they give the right for somebody who discovered a new element to name it. But it only can be named if somebody else has confirmed this, done the same reaction at a different institution. And that's very difficult because it's very expensive to do this kind of research. But we were in the fortunate situation about last year in February, something like this. We made 2 atoms of element 114. And with this, we confirmed the existence of element 114. 2 atoms, can you imagine? And they had an extremely long half-life. They're radioactive, and the half-life of one of them was 2.5 seconds. It lived 2.5 seconds. He said, this is pretty short. I said, no, this is an eternity, 2.5 seconds. Usually they live a thousandth of a second or millions of a second, okay? So, but I could go on forever for this. But with this, we gave the Russians the right to name this. We did another experiment then where we used plutonium-244 to make different isotopes because you have more neutrons. Remember, there are more neutrons in there. It's still the same element, but a different isotope. So we made, we used plutonium-244 and shot it with calcium. And then we made 12 more in an international collaboration in Germany. We made 12 more of element 114 isotope 288 and 289. So we have 4 isotopes so far made. And with this, we proved that this is possible, and the reaction mechanism that the Russians proposed seemed to be working against all the predictions that the theorists had, okay? So far, let's go back to our stardust. We are nothing but stardust, okay? So you have seen now, and today we're going to talk about ionization energies and the shielding of the nucleus by electrons, if you have more than 1 electron. So we talk about multiple electron systems. And we also will talk then about a fourth quantum number. The fourth and final quantum number, it's the spin quantum number. That's what you need in order to describe a complete orbital system, electronic orbital system. So you have seen we have, if n equals 1, you can have 1s because of L. If n equals 2, you can have L equals 0 and L equals 1. So you have minus 1, 0, 1. So you have 2s and 2p, and you can go on. You have 3d. If n equals 4, what kind of electrons can you have there? N equals 4, you have 4s. You have 1 of those. 4p, 3 of those. 4d, 5 of those. And what else? 7 f's. Okay, f, 4f, 7 of those. Okay, you got this. And you see that they are all degenerate. That means they all have the same energy if they are in this quantum level, which is not true. They are not degenerate. The s and p and d orbitals in a certain quantum level have slightly different energies. And why is this? That's a very simple explanation. And if I could have the light, then I will explain to you in an example. So I need some volunteers. One second. I need you here, please. And I need you. Please, you're going to be my nucleus. And you're going to be an electron. All right? Can we have the light a little bit? Wake up, okay? What's your name? Brian, thanks for coming here. So, he's positively charged. Are you sure about that? Okay. He's positively charged. So he's positive, and what's your name? Rena is an electron. She is negatively charged. Okay? What happens? They attract each other. Okay? So you see the full positive charge of this nucleus, and he sees the full negative charge of you. Now, did you volunteer? Okay, come on, let's the second one. So what's your name again? Liz, okay? Liz is now, if you come with me, Liz is another electron. Okay? Come on here, Liz. Follow me, please. So she stood actually very well there. So she stands here, and she sees him fully. And you see the positive charge fully. But you also see her, oh my God, you see her? And she is negative charged, and you are negative charged. What would be the ideal configuration for you that it's that's not a stable configuration? You're too close to her. Where would you be? Yeah, go there, please, okay? So this is now we have n, let's say n equals 1, so we have 2 s electrons in there, all right? Now, he has divided his attention now to you and to you. So he doesn't, so his charge is sort of divided here and there. So see, you only see part of his charge, and you see part of his charge, okay? So now, if you look there, do you see the other electron very well? No. Okay. So this guy shields it, okay? Or the other electron may shield him because you can't see him, all right? So you're going around in this configuration, and since we are an s orbital, we can do the Bohr model on the string. So now let's take a p orbital. So how many nodes do we have here? 0. There are no nodes. You can go rather close to the nucleus, okay? Because there are no nodes. Who wants to be a p orbital, please? Please, go ahead. What's your name? Shivana, come on, be our p orbital. So you can't be here, can't you? No. You can't be here either. You can't be here either. So you only can be here. So how many nodes do you have? 1 node you have, exactly. Do you see him? You have to look through her to see him. So he hardly has any, and you're the same. He hardly has any attraction or less attraction to you. So this is the shielding effect. You shield his nuclear charge, and you experience the attraction, his attraction much less, don't you? Because she's in the way, yeah? So you have much less attraction. So there's the shielding effect. The inner electrons shield the outer electrons. So if I want to remove you, to ionize you, ionization is 0, E equals 0. So she's in n equals 1, you can calculate the energy, minus, so I have to have that energy to go from here to 0 with the negative sign, that's the ionization energy. I have to bring this and pull on her, and now she's ionized, okay? She's ionized. She has nothing to do with him anymore, okay? She's gone out of that system. So there's a hole here. Now you would fall back in that hole, but this is too much, okay? This is too much. So come back, please. So now I want to ionize you. What do you think? Do I need the same kind of energy or less energy? Less energy. Come with me. So I'm going to take you and ionize you. And see how easy that was. She was further out. So I need less energy because she is also in a higher energy level with essentially less energy towards 0. Okay? So we need to, please come back, let's join us. Now, you come, please come with me. Now you're going to be sp, you're going to be a d electron. You barely see this guy in there anymore, don't you? No. Okay? So very easy to ionize you. Okay? Very easy to ionize you. Because the nuclear charge is not as effective on the d orbital, on the d electron, then the p is probably a little more difficult, please come, a little more difficult to ionize. The S, even more difficult, okay? And so this is the effective charge that I explained to you. Give all of them a hand, please. So you've been in orbit, so to speak, today. I shouldn't be doing this. Okay, so if I could have the lights down, please, again. So this is what we do now. You have a multiple electron system, and so far we only dealt with 1 electron system, so this would be L equals 0, would be N1, N2, N3, N4. This would be the 1 to 4 s orbitals. L equals 1. We have now, so the p orbital, the 2s and the 2p, there's a slight difference in energy. The p orbital is higher in energy. Higher means you need closer to 0, okay? You need less energy to remove it because the difference, the number of that level here, if you calculate this, times -1 is the ionization energy. That's the energy that you need to remove it. The energy that it has in this level, you have to take that energy, at least that energy, and remove it, okay? So you can calculate the ionization energy, essentially. Now, the 3s is lower than the 3p, and the 4s is lower than the 4p. Now, let's see if L equals 2, then we have the 3d is even higher than the 3p, and the 3p is lower than the 3s. 3s is the lowest, 3p is the higher, and 3d is even higher. Now, if you look at the 3d here, that's higher than the 4s in energy. Higher means it's less energy. The amount is less energy, okay? Because we start with a very large negative number and we go towards 0. 0 means we have it ionized, has left the building, yeah? Has left the molecule, has left the atom, that electron. So you can see here now the 2p, the energy of the 2p is larger than the energy of the 2s, okay? This energy is larger than this. The energy of the 3d is larger than the 4s, whereas our 3d is here, and there's the 4s. See that? And you could say this further and further. If you go F, it's even more succinct. So you have now seen what the ionization energies are and what is shielding is. And so if you have a one-electron system, that was easy. We use, what is that formula called? What's the equation called again? Bohr's equation, they call it in the book. I never call it this, but I've said it about 100 times that you don't say, what is Bohr's equation, okay? That's Bohr's equation here. And so the ionization energy has the opposite sign, okay? So it's positive because that energy you have to put in, yeah? When you get out energy, any time in chemistry, when you get out energy, you could get out energy, it's negative. If you have to put in energy, it's positive, okay? This is how we define it. The physicists do it a little differently. So you calculate the level, you know what n is, you calculate that energy, and then multiply it with -1, and you have the ionization energy. So we have done this many times, okay? So you can calculate this level here, and helium plus is how many electrons? It's helium plus how many electrons? 1. It's a one-electron system. Z is 2, but we only have 1 electron. There is no shielding, all right? Because we only have 1 electron. With this, you can calculate that too. The ionization energy for this is Z would be 2 would be 4 divided by whatever level you have. For this first level here would be 1, would be 4R, or -4R would be the level. Yeah? So this level is 4 times four times lower than this one here. We have seen this before. So now, in order to ionize this, you would need that energy because you go from the lowest level to the infinity, you leave the system, and this would be 1,000. Remember, this was the Rydberg constant for 1 mole, and we have 4 times that. That would be the Rydberg constant, kilojoules per mole, all right? So there was nothing with it. Now, if we have a 2-electron system, we need to have a helium atom. Which helium atom has how many protons? And how many electrons? Okay, that's a good thing. And they are we say they would be in the 1s, and since there are 2, we say 1s2. That's how we describe this. 1s2 means, the 2 means there are 2 electrons in there. A 1s1, this would be a 1s1. There's only 1 electron in here, okay? So, but now we have shielding. This was the old level. This was the helium ion, this single electron. And it's not quite that well shielded. This 1 electron shields the other one, because then it would be 1, okay? But there is some shielding compared to a 1-electron system. And so the energy here, the energy here, you don't have Z anymore. You have, yes, you do have Z, but you have an effective charge, effective nuclear charge. So you needed to know the effective nuclear charge, but how do you know the effective nuclear charge? Very difficult to get. Actually not. What you do, you measure the ionization energy, measure what energy does it take to ionize your atom, and then you can calculate the effective charge. You have this and you have this, and you can calculate the effective charge. So the ionization energy for the real helium atom with two electrons would be a little bit smaller than double. Remember, before we were 4 times, and so there is a shielding effect. So if you have now, for example, a 1s, there's 1 in here, and the 2p1, the ionization energy would be, if you go from the 2p1, so you have 1 here and 1 here, 1s1, 2p1, so that would be in this level, would be the same, the ionization energy, if you would have a hydrogen n equals 2. It would be 328, just to give you an example, okay? So now, I want you to think very carefully, to think, really think, show me that you can think. And forget what all the stuff I said today. Remember the stuff I told you the last couple of times, okay? Now, we have hydrogen, a helium plus, and the lithium 2 plus. The hydrogen is in the 2p, the helium is in the 3p, that electron, and this is in the 4p orbital. I'm asking you now, which atom or ion has the lowest ionization energy? The lowest ionization energy, okay? So why don't you think about it and give me your answer. Don't fall in the trap, okay? I gave you a hint already. Pretty subtle hint, actually. I would find out how many electron systems these are, okay? A 3 electron system, 2 electron system, 1 electron systems. You fell in the trap. Or you don't know arithmetic. One or the other. I hope it's not both, okay? So, how many electron systems are these? These are 1 electron systems. So what is n here? What is n here? What is n here? Why don't you put this in here and calculate it and give me the answer and tell me which one is the lowest energy system? Okay, discuss it with each other, please. You need to discuss this. You need to get that right. Yes. Yes. Good. Because in the morning, I think it was the Monday. They still didn't get it the second time. Most of them. Some of them. No, I don't want to insult them. There's nothing, no comparison. Period. Okay? So 75% say A. All right? And I agree with them. So why don't we do that before I even put the solution up here? Okay? So what is... this one here is 2. So the H is minus ionization energy. We can forget that minus. So that says 1 squared divided by 2 squared, okay, is 1/4 R. 1/4 R is 0.25, all right? Now this one here, what would that be? This is 2 squared is 4, that's 2, set is 2, times 3 divided by 3 squared is 9, minus 4 9, plus 4 nines, what is that? 4 nines is 0.44, isn't it? All right. Now, the last one is n equals 4, z equals 3, so this is minus 9/16 minus R, or this is plus 9/16 R. We're talking about ionization energy. So 9/16 R is 0.56. You should know this from the fractions, but I just made sure that you understand. 0.56. So which one has the lowest energy? 0.22 R, 0.44 R, or 0.56 R? All right, this was this one. Now let's go and do it again here. Ionization energy, that's what I just did here. See that? That's what I just did here. That's what I just did here. So which one is the lowest energy? This is the lowest energy, and with this was the answer then. Okay, good. Did you get that? You need to know this stuff, okay? So now don't forget what I told to you, and don't calculate, because you can't. Don't forget what I said. Never forget what I say to you, but don't forget what I said to you today. Now you have to remember what I said to you before I started these camp quizzes. We have an atom, and which one has the lowest ionization energy? We have hydrogen atom, 2p. So the electron in the hydrogen atom. We have helium atom, a 1s and a 3p. We have a lithium, 2 in the 1s and 1 in the 4p. Which one has the lowest ionization energy? Which one has the lowest first ionization to remove 1 electron? Okay? Which one? Now think about what I explained to you here. Which one would that be? Would it be the lithium, the helium, or the hydrogen? Why don't you think about it and give me your answer? Now we do have shielding now. Before we had no shielding, because we only had 1 electron. Now we have more than 1 electron, and there's shielding. There are lower orbitals in the way of higher orbital electrons. Very nice. Good. Okay. Now, that was the first question I had. Okay. So let's talk in terms of football. Yesterday was football. Okay. So this is blocked by how many? 3 blocked by how many? 2. This is 2 blocked by 1. and this is 1 blocked by nothing. Okay? So why don't you discuss this? I need to get these 68 people on the same side. Don't vote with the majority. Understand it, okay? Why don't you talk to each other for 1 minute and see if you can? It doesn't really matter. Everybody will click C. So anyhow, but make sure you understand it. Talk with your neighbor. If you didn't understand it, perhaps she or he will be able to explain it to you. I give you 1 minute. No, I give you even 1.5. It's important that I just explained it to you, okay? But make sure that you understand. It's not about the right result. Wow, what a surprise, huh? Okay, so I said it, so we could also go this way. We said the effective charge, if we just do this, the effective charge is, this is the charge is 3, but it's blocked by 2, so this would be an effective charge somewhat around 1, okay? And this is far out here. This is far out already, that electron. It's in the 4p. It doesn't feel that charge of that 1 effective charge, doesn't feel it very much, doesn't experience it very much because it's so far away, okay? So this one here is the charge is 2 of the nucleus, and we have 1 blocking it, so we could say effective charge of 1. Of course, I've shown you it's not 1, it's a little bit bigger. But this one is 3p, and it's also relatively far out, but here I have not this much blocking here, and this is further out. You see that? This is further out than that one. So if the effective charge, I say, is here is 1 and here is 1, this one will experience less of that effective charge than this one. And this one, there is no blocking whatsoever. It's just a little bit further out, and this is the effective charge is 1 here, and this is the real charge, and this would have the energy. So now you could calculate this, the ionization energy, and this is what I ask, which one has the lowest ionization energy? So if I say this effective charge would be 1 about, just to calculate, all right? You don't have to calculate. This would be about, this would be 1/4, this would be about, what would that be? The 3p would be 1/9, okay? Because the charge is 1, and this would be the 4 1/16, okay? So this one would be probably the easiest one to remove, okay? And with this was the answer. So now we come to the 4th and final quantum number, which is the spin quantum number. Electrons behave like magnets. They orient themselves in an electric field, but they behave like quantum magnets, not the magnets that you know. You remember when you take some magnets, you have a magnet here, and you put another magnet here, and you move that, the other one moves with it, okay? And regular magnets, non-quantum magnets, they move 360 degrees. You can do this with iron powder, put iron powder on a magnet, move it around, it moves, they orient themselves, and they move with each other, all right? So this is what you see, for example, if you have a conventional magnet, a classical magnet, you would see a distribution. You shoot this through a magnetic field, and you see a distribution of hitting the wall or whatever, would be like this. If you have quantum magnets, you don't see this distribution, and electrons are quantum magnets. That's the weird part of it. So you see 2 distributions. Quantum mechanically, you have one here and one here. And this is because the spin is quantized. There's only two possibilities you can have for that spin. You can have magnetic quantum number can be s equals plus 1/2, would be spin up. And now the other quantum number would be what? Minus 1/2, spin down. Okay? It doesn't do like real magnets, it goes like this. It only can have this or this quantum state. So with this, you have two possibilities of filling electrons in an orbital. You have the energy, you have the shape, you have the orientation, and you can put a total of two electrons in one orbital. One up, one down. Okay? And with this, we have the fourth quantum number. You already get the hang of it. Obviously, there's only two electrons possible per orbital. All right? Because one can only be up, one can be down. They can't be both up in the same orbital. So that's what the Pauli exclusion principle says. This guy Pauli was a physicist. He says no two electrons can have the same set of quantum numbers. All right? They can have n the same, L the same, m sub L the same, but not s, m sub s the same. You can't put two with the same spin in the same orbital. All right? And so when you have, for example, let's say it would be, I think I should draw three. Let's say this would be an orbital and a orbital where we have two possible orbitals. Shape would be better. If I had three, it would be better, but it's okay. So they have the same energy. So the px, the py, and the pc has the same energy. Okay. Now you have to fill in orbitals into the electrons into the p orbital. So you put one in px, and you put the second one in px. One up, one down. That would be this here. Okay. This is a higher electronic state because it's this energy, the pairing energy you have there. And the other possibility is that you have one in the px and one in the py, but one is up and one is down. All right? That also takes energy. Actually, it takes light. You can flip it. If you have that and you put a little energy in there, you flip it into that state and it flips back. This is why liquid oxygen has color, because it does that spin flip. I will show you liquid oxygen, and when we come to the oxygen, I show you how this can happen. So this is too high of an energetic state. This is too high of an. Now this would be the right way. You put both with the same spin in the same kind of orbital, different orientation. Actually, if you have the p orbital, you put one in the px upspin, one in the py upspin, and one in the pc upspin. Okay? So they have to have the same orientation. Now let's see, we're taking a bus, okay? And the bus has two seats here and two seats there, and you're walking in and sit down in the first seat, all right? Of course, you don't sit by the window that nobody else can sit next to you. And so now the next guy comes in, he sits in the next seat, and then the next seat, and the next seat. Except this one guy who comes in and wants to sit right next to you there where the window seat is open. That would be extremely weird. It would freak you out, okay? They said, my God, what's the matter with this guy? Yeah? And so the bus fills all up, single row first, and then when there's only the empty seat next to somebody, then it fills up double rows, okay? This is what you usually, except you have a couple of buddies there. They make a lot of commotion under the bus. That's a different story, okay? I take the 51 sometimes, and so I see the okay, everybody goes to Safeway, I think, or somewhere. And so this is the Hund's rule. This is actually manifested in the Hund's rule. Degenerate orbitals, that means orbitals of the same energy. P electrons have the same energy, or d electrons have sort of the same energy. Degenerate orbitals, they always fill with parallel spin. The parallel spin in each orbital is the lowest energy possibility, okay? So this is called Hund's rule. degenerate. So this is not a good energy situation. That's not a good energy. That's the lowest possible energy situation that two orbitals could have when they're filled with two individual electrons. All right, so we talked about the bus. Let's see what else we can talk about. These particles with half-integer spin are called Fermi ions. Okay? They follow Fermi Dirac statistics. All right? So protons are Fermi ions, neutrons are Fermi ions, and electrons are Fermi ions. Okay? They have half-integer spin. And they all follow this Pauli principle. There can't be only two with the same spin cannot be in the same energy level, in the same quantum orbital. All right? So, but then you have these other ones. These are full number spins. These are called bosons, not bosons. These are bosons. There was the person, Bose, you know, the guy who makes the fancy radios. Actually, that's the name, Bose. You don't know what a Bose radio is? Yeah, okay, good. I thought I'm that old already. So these are bosons. They don't follow the Pauli principle. And so Bose came up with this, and Einstein then he verified it. And this became the Bose-Einstein statistics. And they can all condensate in one very low energy level. For example, if you use helium, no, I don't want to do anything here. You do helium, and, oh, great. Okay, you use helium at a very low temperature, at 2 degrees something, below 2 degrees, then all the helium atoms go in this one state. And they can put them all in one energy state. It's impossible. These are bosons, and so this is called a Bose-Einstein condensate. And the point is, when Bose came up with this, so I'll tell you a little bit about publishing. When you're a scientist, you have to publish. You have to let the world know what you have done. And also your boss wants you to publish, because the more publications you have, the more famous you will become. Not necessarily, they have to be good also. But so you write up what you have done scientifically, and then you send it to a journal. You don't send it, you go to an internet portal and then submit it. And then there's an editor on the other side, and they all do this for free, most of the people. And then this editor will assign this paper to another scientist who is an expert in that field, and that expert will write a comment. Will you read this very carefully and write a review and say, you know, this is right, or this is wrong, you know, this is unacceptable. And so that's what happened to Einstein. So this Bose paper was submitted to him, and Einstein said, I really don't understand it, but everything seems to be correct in that paper, so publish it, all right? And so, of course it was right, and so this is how this Bose-Einstein paper was published. And very often that is, of course, the problem. If you have something so new, there are no peers who know about this, who can judge this. And sometimes you discover something, and they say, the people who don't know anything about wait. The people who don't know anything about it, they say, you know, can't be. And then you don't get it published. Now let me show you one thing. These fermions, these half-integer spin. So if I turn around 360 degrees, I have a full turn, and you see me fully again. Now if I could have the camera, please. Now you see, that's a fermion. And this is how you call this sphere? Möbius sphere, exactly. It's a Möbius sphere. It has this funny shape. So, and this is how they move in space, actually. The quantum particles, you go around 360 degrees. You see that? We were blue before, and now we are downspin. Now I have to go another 360 degrees on my Möbius sphere, and then I'm there where I started. Okay? Weird, huh? Isn't that? And with this, we talked about Fermi ions, and we talked about the fourth and final quantum number to describe electrons in a system. Okay, good luck tonight.